All right, welcome everyone. Our team name is Planiac.
I'm Connor Adams. I'm Nick Herman.
And our advisor is Dr. Moon. And today we're excited to present to you our automatic paper airplane manufacturing machine.
So our goals in coming up with the project was to decide on a project that would make use of everything that we've learned, be a complex mechanical and electrical system, but also it would be pretty fun. Here is the design we ended up we have for you today. I know it's a little bit hard to see, but we're going to get into the 6 individual stages of it in more detail a little bit down the line.
So the requirements of this project are we want a machine that we can put unfolded paper into and get a completely successfully made paper airplane out without us having to fold anything ourselves. We've taken a sheet of paper that's half the size of the standard US printer paper, and I'll put a plane that we can throw. We're defining a successful plane that is one that if you throw it would fly for 10 feet and also needs to look like a plane. It can't look like a paper ball or any kind of mangled monstrosity. It has to look like a plane. We want the machine to be able to detect when it is jammed and stop automatically. We also don't want this machine to just rip up and eat the paper. We want it to actually make the product. And with that, the machine needs to be easily serviceable because it's going to jam. We want to be able to get the paper out of the machine before it causes any damage. And we want an output rate of at least 2 planes per minute, which is on par with how fast a human can fold a paper airplane. So we're designing our models in 3D, and our design intent when we made the models were to be 3D printed. So we're avoiding things like overhangs and on those to be small and large parts. We want the wheels to be able to grip the paper, but not destroy the paper. They just put it that way. We're incorporating components like servo motors, stepper motors, and several different ultrasonic sensors, and we're going to connect them all with several Arduino controllers. The first stage of this is the paper feeder. This is where you load in the paper and it dispenses it into the system. This is made of 7 main components, 3 of which are a sensor mount, which will be detecting how much paper is into the actual machine, and will notice when we run out of it. Then a motor plate, which will rest on top of the paper, shown over there. It will dispense a single piece of paper onto the rank, which will enter the system. Some of the challenges we've had with this design so far is designing proper clearance for the motors so they actually sit inside of it, and making sure that we're only inserting 1 piece of paper into the system.
Yeah, so the second stage of this is going to be our first actual folding portion, and that's going to be our 45-degree bend. This is currently a servo design, and we are going to be inserting our piece of paper into it to our set distance, and then the servos are going to actuate, and they're going to bend over and bend the piece of paper into our 45-degree shape. This consists of 3 main parts. That's going to be our base plate, our brace that kind of holds the piece of paper in place, and our 45-degree plates that are attached to our servos that are going to bend over and bend back. Originally, we had a mold design. Instead of those 45-degree plates, they were not servo-driven. Our original plan was to push the piece of paper in, and it would push into this cone shape, and it would bend the paper up and over. And as you can see, we did print that. We did prototype that. We had a lot of issues with just not getting a consistent fold, and it was also very hard to get a nice actual line on there. And additionally, there was a lot of possibility for it just crumbling as soon as we inserted it. We did have a little success, but it was not reliable. So what we went with the servo design. Additionally, when we 3D printed the servo design, originally our rods connected to our servo motors were 3D printed, and what we saw with that was they suffered from a lot of torsion and a lot of kind of preemptive bending, and we didn't foresee a long lifespan. So we ordered these 3mm carbon fiber rods, and so far we've had really good success with these not bending new as much as the old ones did. But additionally to that, we have a brace that's very important because when we first designed it, we did not have that, and we had struggled getting our very precise folds. The paper would shift a little bit, so with that brace, it allows us to make very precise, repeatable folds over and over again. And then this is what our piece of paper is going to look like after that first fold. Our third third stage, second fold, is going to be our 67.5 fold. And this works very similarly to the first one. We have not printed and tested this yet, but we do anticipate it to work just as well as the first design. It has pretty much the same design challenges as the first one, but with the addition to, because the 67.5 fold is so much longer than our 45 fold, it gives us a really large area that we could have a dead zone in if our pickup wheels are not positioned correctly. So it was a very, very big design point to have them close enough together that we're not going to get a piece of paper stuck in between when we're not making original. Additionally with that, we have a lot of clearance issues with 3D printed parts. When we first printed these, you take a look at those. We did have to do some manual clearancing just because of just the not precise process of 3D printing. There was a little bit of warping, and we had a lot of parts kind of colliding with each other. So we do need to keep in mind the design around that in the future. This is what it's going to look like after that second fold.
Then, in that shape, the plane will fed into stage 4, which is the half fold. Here we opted for a chute-based design, which has 2 drive wheels at the front of the chute that pushes the paper up through the chute. And due to the shape of the chute, it just automatically folds the chute in half down the center line in the middle. And then it is run through 2 rollers that spin in opposite directions to crease the paper and push it forward into the next stage. Some design challenges with this, like Nick mentioned, we had ideas to use chutes a lot earlier on in the project as well, but they just tended to not work out the best when using paper. It just tends to bind a lot. So this is the only place where we found a chute might still be viable, and so far it's looking hopeful. Finding the length, much like with his problems, finding the length between the drive rollers and the crease, so the paper would not actually make it from one roller to the other side, was also important. And it will come out looking like that, folded in half.
So after that stage, we have the last folding stage, which is the white press. I actually have that printed out right here. The paper airplane will enter the channel at the bottom, as shown up there, which is driven by a pulley system to actually move the paper and stop it. From there, the top part of the press will kind of come down using the threaded rods, and we'll squeeze and fold the ones onto the side, lift up, and let the plane exit the move. And then we're ready for the last stage. Some design challenges we had for that were getting the proper clearance for the gear system and the pulley system in the same spot. We have managed now, but it was certainly a challenge to fit those two in. Not to mention the speed we wanted the press to actually be able to close and open relatively quickly, so we do have to issues that want to close faster than normal. And the one thing we're taking advantage of is that the spring back, if metal has spring back, and so does paper. And we're going to be exploiting that so that we can go to the next stage without the windows kind of interfering. Because we don't want the ones to fold like this entering the final stage. We like that they kind of spring back after we fold. And that's the paper representation.
So yes, then that gets fed into stage 6, which is the airplane launcher. Like Anthony mentioned, we want the wings to be able to just naturally bend up and out of the way of the pulleys that are going to carry the plane along the bottom ridge, accelerate it, and send it out forward to actually let the plane fly. It's essentially just 2 parallel belts driven by a motor, which it is important to note that this is most likely the motor, not the motor we're going to use for this step, but it's a good example of where the motor would go. This motor, this Lima stepper motor, we do not expect will have the RPM to actually get the pulleys rotating fast enough to watch the plane. And it's also important to note that we don't consider this an essential part of the airplane manufacturer device. This is just kind of something that we can add on to the end if time allows. That would be a little bit more fun than just the machine just kind of plopping out a paper airplane onto the table.
So for the computer design process, we ended up choosing to use 2 Arduinos for this process. Now, we did that because 1, we had 2 Arduinos on hand from the robotics lab, as well as we need a lot of inputs and outputs to drive all these servo steppers, motors, and sensors. So we broke down to 2. Our first Arduino is going to be more of our motor Arduino. So it's going to drive our servo steppers and our DC motors. It's going to be starting the fold, that's going to be, and then it's also on a timer, and it's going to move from stage to stage. It's important to note that we're going to design this in a way that all the stages are going to take the exact same amount of time to finish up. So if the press takes 8 seconds, but our fold takes 4 seconds, we're going to artificially slow down that fold stage so that we have a steady flow of planes going through this. For our second Arduino, it's going to be our sensor Arduino as well as our emergency stop button. The sensors are going to be ultrasonic sensors, so they're going to be sensing when the paper is there or is not there, and we're going to set that up on a timer system so that if it crosses one sensor but does not reach the second sensor in a set amount of time, that's going to be our kind of like crumple detection. The paper did not reach the other end, and we are going to use that to stop the process immediately. Additionally, we're going to be using that to have our emergency stop button. So in case anything happens, you can hit the button and it will send a signal to the step motor controllers to stop immediately, and also it will feed back to our Arduino 1 to stop that process as well. So for the wiring diagram, I put a simplified wiring diagram up here just because of how many step motor controllers, DC motor controllers, and different outputs we have. It was very hard to see individual parts. So I broke it down to inputs and outputs for the Arduinos, as well as sample connections for our separate motor controllers and our motor controller. So as you can see, we're using the L29 DC motor controller for the robotics lab. The A4988 stepper motor controller, which we ordered on Amazon to control our stepper motors. The Parallax standard servos from the robotics lab, and the HC SRO4, which are some of the sensors from the robotics lab as well. And we anticipate we're going to order a couple more of the ultrasonic sensors just because of the sheer amount we need to do.
As you can see in this table right here, this is our fall semester schedule. This table contains all of the deadlines that we had to meet during the past few months. It basically highlights the engineering process thus far, leading up to the final design presentation. This semester mainly consisted of planning and bringing together ideas and brainstorming new ones. Now, as far as leading into this presentation, we'll lead into the spring semester with our final design. This semester will contain mostly designing, testing, and prototyping. Now, a system like this requires a lot of design, testing, and prototyping, so we anticipate that many of the dates on here might be changed to modify more design and testing as we need. This diagram represents our work breakdown structure for the system. Each of the categories up there is labeled and basically outlines all of the different systems that we have inside of our system. So basically to organize everything. This is the budget so far. It's a little table that comprised of all of the different parts that we have. Now it's important to note the right side, the column over there, actual cost versus total cost. The actual cost represents all the parts that we have in our inventory, and the total cost represents what these parts would cost if we were to order them, but we do have two separate ones. Now as far as ethics go on this project, we're mainly abiding by the ME rule of ethics, keeping paramount the wellness and safety of as far as future plans and testing go, we plan on dedicating the entire spring semester to this, to perfecting our design and further improving on the scope of the project.
As for testing plans, we'll be testing each individual stage, making sure they work, and then the whole system together. Testing to make sure that it works properly. We can get into each individual stage works first, then we'll have a lot less trouble with the full assembly.
Thank you all for listening. Any questions?
So, you see, always great innovation starts with a great idea. I think this space in my career. But I'm really liking, don't get me wrong, I'm really think about this. What you guys are trying to do is to create a machine that replaces traditionally people consider not impossible for a machine to do, which is a manual dexterity of your hands. You understand? That's the backbone of this project. So you guys are actually solving a very, very important problem. So I was joking with you when I said that. I was not impossible. You can fold anything. You can fold whatever you want to fold. We can do that. So that's what this is about. It's never just about airplane. Airplane is just something you're dealing with right now. If you have this technology, you can fold whatever you want to fold. That's the application that is needed. Right? Sky is a needed for that. So for that, I want to compliment you guys for this great idea. It's really using machine to do this. That's traditionally not possible. That's a great idea. Okay? So first off, it's just a practice side of this. So, I mean, the control, I'm pretty sure you guys can pull this off, but so how do you deal with jams? If something goes wrong, you can't just plan for perfect day. If something goes wrong, what's the plan? How do you deal with it? Like, you see what I mean? Like, is there a trigger or something tell you something didn't go through, somewhere gets stuck in the middle, and how do you proceed?
Yes, that's what we have the ultrasonic sensors for. They'll be sensoring distance in the machine, where there will be a clear through vision that they usually have, so we'll be sensing whatever the distance is to the ceiling normally. And when paper passes over, it'll be a much smaller distance. So if it does not detect that change in distance, then the machine will stop.
Okay, so the machine will stop by that. You just manually go there to retrieve, to try to retrieve and start again. Is that
But it will stop by that.
Okay, very good. Otherwise, you're going to have a paper bowl, you know.
This is something we didn't model yet, but we plan on modeling in the future.
Yeah, okay, so it's fine, because to retrieve that, like using the machine automatically, it's not easy. Like, if your printer gets jammed, you have to go there, open it, and take it out. Like, no, we cannot make that automatic. It's super hard. So as long as you have a plan, it tells you it doesn't fade continuously when it's jammed, then that's a good plan, okay? Very good. So again, like as generally speaking, it's low risk. You guys have put, it's not easy. We absolutely have to pull it off because we don't have a very high power stuff. So it's everything else just as long as you're serious about this, you can pull this off. You can make this work. I'm pretty confident about that. It's a very interesting project. Really like long term. Hopefully you guys can, again, the idea is always about future. This technology can go a long way if you harness it properly. Very good.
That launcher is critical to your marketing this product when you get done. Because seeing those things sail is really going to impress people.
Yeah.
I want to make a suggestion on that. You were concerned about the speed with which you launch them. Use a series wound motor because that gives you maximum torque at low speeds. Much more so than just a permanent magnet motor. So that's something you could consider, and you can give it a big wall of voltage at zero speed. It's going to take off. So just a suggestion.